All right. Yeah, I'm here to talk about a really severe test method for ASR, so don't throw things at me. My branch chief is here. That's not a good look. This presentation is it's a compilation of a lot of different things that we've thrown at autoclave test methods over the last decade or so. I'll try to answer questions to the best of my memory. The motivation for this is the same motivation we have for all of these test methods. We have two standardized test methods for ASR that we use. Both are problematic. We need something fast and reliable. You guys are probably familiar with these, but the 1293 concrete prism test, I'm just going to go over them because I'm going to compare to these a lot, is a one-year test for Portland Cement. I know they're pushing, if they haven't already, if it's not out yet, they're putting the type 1L in there as well. For 2 year, it's a 2-year test if you want to do something like SCMs, fly ash, coal ash, silica fume, whatever. So these aren't this is not a practical test for any construction project, but especially, so at ERDC, we are supporting the Corps of Engineers. So when you think about traditional Corps of Engineers, you're talking about locks and dams, mass concrete, mega concrete projects that provide safety and economy to the country. But we're also supporting all branches of the military, and a 1-year test is not going to cut it. 2-year test is not going to cut it for the U.S. military. 1260, 1567, so one test aggregate reactivity. 1567 is if you want to use SEMs. 14-day test, we know that it's plagued with false positive, false negative results. We do use these. We specify this for all of our projects. However, for some applications, so if we're thinking about air-filled pavements, we get really conservative with these limits. We extend the test out from 14 days to 28 days, and then we reduce the expansion limit from 0.1% to 0.08%. And we are very purposely conservative because if we have ASR in our air-filled pavements, we get spalling that leads to FOD, foreign object debris, gets sucked up into our multi-million-dollar asset jet engines. That's a bad thing. So we do exclude a lot of aggregates that may not be problematic by doing this. So the overarching goal of everything that I'm going to talk about today is just validating autoclave test methods, and I'll get to what they are. And where we are now with this is I'm not trying to convince ASTM to push this through. I know that takes a lot of work, and it takes a lot of, well, people yelling at me for how severe this test method is. But we're at the point where the Air Force is interested in using this if we can show that it's at least as reliable as 1260, 1567. For some projects, we need them faster than that 28 days even. And especially if you test out to 28 days and something comes back and you have to adjust the concrete mixture proportions, you've just set yourself up for another month for an air-filled pavement, and they really want to cut down on that. So we're looking at autoclave test methods to get that done within a week so they can make fast adjustments. Autoclave test methods go back to the 80s, starting in 1983 and up till 1996, where they were using mortar, so we're limited to fine fractions and mortar bars, and then beyond that, we started looking at concrete prisms. I really want to focus on these two test methods, the Laval-Canmet method from Benoit Fournier. That's a mortar bar test. It's 5 hours inside the autoclave at 130 C. That's really high. These are the same mortar bars that you would use in 1260, 1567, except that we are boosting the alkalis by adding sodium hydroxide to the mixed water. And we're adding sodium hydroxide to get 3.5% equivalent alkali content. It's a lot. So like I said, these go inside the autoclave for 5 hours at peak temperature. It takes 3 days from mixing, and the proposed expansion limit is 0.15%, so anything above that would be considered reactive. And then Eric worked on a test method at UT Austin, and then I kind of helped validate that through my dissertation work. That's using concrete prisms that are like the same ones that we use in 1293, except we're boosting alkalis to 3%. I know this is infuriating to see 3.5 and then 3, and then 130 and 133. Yes, I still flip them 10 years later. So same prisms, they go inside the autoclave for 24 hours at that peak temperature, and then it's a 4-day test from mixing to results, less than a week. The proposed expansion limit for that was 0.08%. Through my dissertation work, we raised it just a little bit to 0.09% to make sure that we're really just keeping those non-reactive aggregates, the ones that we know are non-reactive, below the threshold. There is some inherent expansion in this test method. So this is the process. Over on the left, that's an autoclave. These are commercially available. They're not that expensive. They don't take up a huge footprint in a lab. I don't know what they are cost-wise post-COVID, probably like 3 times what they originally were. So these are used to clean medical equipment, lab equipment, and as soon as you put concrete and mortar in there, you void your warranty. So if for some reason the door gets stuck, you're spending your Saturday taking apart an autoclave instead of enjoying a football game, trust me. This is showing concrete prisms, but like I said, we do have a mortar bar test. They go inside the autoclave in this little wire basket, and we thread some metal wire between them so they don't move, they don't touch each other, they don't touch the sides of the autoclave. They're not resting on those gauge studs. There's actually a little hole that it goes into. And then we put deionized water in the bottom, and that creates a steam environment, a little bit of a pressurized environment. We measure the prisms and the mortar bars before they go in at room temperature. The autoclave lets you open it up after it's, I think, at 80, 90 degrees C, unless you just want to waste your Saturday. It lets you open the autoclave up at that time, and then we take them out. We put them in preheated water, so at the same temperature that they are already, and then we slowly cool them, water cool them over time so that we don't induce any thermal shock, and then we measure them again at room temperature. All right, so we talked about the history of it. This is some of the more recent work. Like I mentioned, when I was at UA, I was validating some of these test parameters. We did look at alkali leaching involved in the test method. It's on par with 1293. Everything in the dark gray is what I'm going to kind of touch on in the next few slides. We did look at the presence of ASR through SEM. That's all preliminary at this point. And then while I was there, I was working with Jenny Tanner at University of Wyoming. And we did some things together. We were testing the same aggregates, but they've also had other drivers for what they were doing with the autoclave. So I'll touch on how they tested combined aggregate fractions. And then they have some field exposure blocks that are about at 12 years at this point. And then, sorry, dry mouth. At ERDC, we recently did a very small study, throwing some more things at it. That was an 18-month project. I looked at some fly ash preventive measures. I tried to pick some bad players out of the aggregates that maybe passed the mortar bar test, the 1260, but didn't do so well in the field or in the CPT. I did look at reducing the cement content for job mixtures as the first step, and spoiler alert, the workability was terrible. So I think we're just going to stick with the standard test method. All right, so first let's start out with just some overall data. This is a lot of what I did for my dissertation work. Over on the left, we're comparing the autoclave concrete prisms to 1293 expansion, and this doesn't cover all of the aggregates we tested, just some of them. The solid markers show coarse aggregate fractions, and then the empty markers are showing fine aggregates. Overall, we get 85% agreement between these two test methods, but we get a higher agreement between coarse aggregates, 93%. So that's just whether or not they are reactive. You can see the different classifications. So we've got a different expansion. This is from 1778, ASTMC 1778, where you have non-reactive, moderately, highly, and very highly reactive ranges for 1293. We do that a little bit later for the autoclave as well. Fine aggregates, however, in the concrete prisms don't really agree as well. You can see that those expansions are pretty high, even for the non-reactive. And I'll touch on that in just a second. Over on the right, that's from the University of Wyoming. This is, that's showing coarse and fine aggregates that were tested. They've got an R-squared value of 0.8. But they were seeing the same thing that we were seeing with the fine aggregates being just really highly expansive. If we have anything that's siliceous or remotely reactive, they just don't do well in a 24-hour test duration. So that led us back to the Laval-Canmet method for fine aggregates. So we're back to mortar bars to test fines. On the left, it's showing our data for these 20 aggregates compared to ASTMC 1260. All of those error bars are showing ranges. So this is where we did the multi-lab study for this method. We had pretty good CVs for that test, but we had 7 labs that were participating, and these are kind of just averages from those 7. Our non-reactives down there are playing well in both test methods. We do have one aggregate, one moderately reactive aggregate that is right there on that line for 1260, but it is showing up as reactive in the autoclave. That one is reactive in the field, so we're able to pick that up where it's maybe not showing up as well in 1260. We do have some 2 moderately reactive aggregates down there that are not failing the autoclave, but they do fail 1260. One of those is at least 95% crystalline quartz. I couldn't find any field data for these, so I don't know if they are false positives or, false positives in 1260. It appears that they don't really have any issues in the field, so maybe that's why we're not seeing that expansion in the autoclave. Over on the right, that's showing the expansion for the aggregates that we had 1293 data for, where we've got one non-reactive that's playing well. I do have to apologize. This non-reactive aggregate that is showing up in 1293 but not in the autoclave, I promise that's an error. I don't own any stock in autoclaves. I'm not trying to tell you that like this works. That really is an error. That shouldn't be there. But we do have, again, a moderately reactive aggregate that is being picked up by the autoclave and not the CPT. And we do know that that one has caused some issues. Some preliminary SEM work. Part of this, the most recent study that we did at ERDC, that 18-month study, we were planning to do some more SEM work, but for the entirety of the project, our SEM was down and being repaired. It's back now, but conveniently it was down that entire time. So this comes from my graduate work. On the left, that's showing the highly reactive Job sand. So that's a sand particle with an infilled crack in it that looks like it's ASR. And then on the right, that's Placidus, a very highly reactive coarse aggregate, where we have cracking of the aggregate and what appears to be ASR gel in the concrete, in the cement matrix. We've got more to do with this. I'm curious to see what it looks like with some of these slowly reactive aggregates or non-reactive aggregates even, to see what we're doing. This data comes from University of Wyoming. So WYDOT, the Wyoming Department of Transportation, funded a lot of their work at Wyoming. For them, they were interested in testing both the coarse and fine fractions together in concrete prisms. And I think that's just the nature of how they do some of their projects. They're using the same aggregate, coarse and fine fractions. So Wyoming looked at testing coarse and fine separately and then combining them, and these are the correlations that they get between the autoclave and the CPT. This doesn't show those really highly reactive fines, though. I think, Eric, I think you're on the paper, right? That this is going, yeah. So questions about this can go to Eric. Here are the field exposure blocks that they've done. They've got unboosted and boosted to 1.25% equivalent alkali content. They're comparing that behavior to the CPT and I know this is also confusing, ACPT, that's the autoclaved concrete prism test, not to be confused with the accelerated concrete prism test. I'm not discussing that one at all. So we do see some agreement. Those first 3 in the table, those first 3 aggregates were showing some issues in the field, but they were passing the CPT. You'll have to talk to Jenny about where the autoclave data is for those, but they are seeing reactivity in their blocks. There's some agreement there with the HPC aggregate that's non-reactive across the board, with the KR aggregate that's highly reactive across the board, and you can see that their fine aggregates are really kicking off in that 24-hour test. All right, finally, this is the 18-month study that we recently did at ERDC, and when I went to choose aggregates, I used the Federal Highways report that I'm going to reference at the end that came from UT Austin work, where they did their field exposure blocks and did 1260 and CPTs. So I tried to pick out a couple of aggregates, the C2 and the C5. These are all coarse aggregates. They're all going into concrete prisms, so we're talking about the 24-hour test. I tried to pick out 2 aggregates that passed the 1260 but showed, reactivity in the field. And we know these are reactive and they do show up in the CPT. Just curious to see how they would perform in the autoclave. At the bottom, those are those reactivity classifications. Those come from C1778. And then the ones for the autoclave concrete prisms and the mortar bars, those came from my dissertation work. So this is comparing the autoclave expansion for these aggregates in concrete prisms to the AMBT, so the 1260 performance. And our non-reactive is playing really well. We do have a borderline aggregate there, C2, that's showing up as reactive in the autoclave, and it's approaching the limit in 1260. We do know that that one is reactive, but it may pass 1260. What you'll notice too, because we're using data from the literature, and we did run repeat autoclave tests. That's why you see the vertical alignment with the results. You're probably seeing aggregate C3 and C5, where the repeat tests look different. We've got very highly reactive or highly reactive behavior in one test, and then when we test it again, we got actually non-reactive behavior. This was the first time I've seen this in autoclave tests. In all of the aggregates I've tested, I'm not sure. I'm still tracking down what happened there. I do think that those non-reactive results are outliers. I'm just not sure what happened. We had some new technicians come in, and so it could just be something to do with learning how to do this method. And then on the right, we've got autoclave expansions compared to the concrete prism test. Again, non-reactives are playing really well. We do have some pretty good agreement between at least non-reactive and reactive, especially if we ignore what I do think are outliers. On the left, we're comparing autoclave expansions for these to the field exposure blocks, and we are getting agreement at least between reactive and non-reactive. And then on the right is showing concrete prisms, where I threw in 25% class F fly ash just to see what would happen, and a little surprised to see it did suppress expansions in 24 hours. So I'm comparing the fly ash to the standard autoclave expansion without fly ash. We've got a little more to do on that. I'm curious to see what some other SCMs do, especially something like a silica fume or some sort of, some of the new pozzolans that are coming out, and seeing what they can do in 24 hours in this really extreme test. So we do have some conclusions at this point. We know that we need two different test methods if we're looking at coarse versus fine, because the 24-hour test is just too severe. We are seeing ASR, at least in the highly reactive aggregates that we know we should be getting at ASR. So far, the accuracy, if we ignore those two really bad outliers, the accuracy appears to be at least as good as 1260, and we are in fact picking up on some aggregates that pass 1260. I didn't present on this, but the multi-lab precision for the Laval CanMet, the mortar bar method, is on par with 1260 and 1293. That's a good thing. And we did see some suppression of expansions with the Class F fly ash. So moving forward, what the Air Force would like to do with this is specify autoclave test methods as an alternative to 1260 and 1567. Just have it in the specification. You can still do the others, but if you want, you can do the autoclave test. We've got a few things that we have to do first to get there, resolve those discrepancies with those repeat test results. We don't want anything coming out non-reactive if it's not non-reactive. Like I said earlier, look at some other preventive measures. We need some more petrography. I want to see what's going on inside, especially for non-reactive aggregates, to see why we do have that inherent expansion, and see if we can pick up on some slowly reactive aggregates as well. And then, so that takes me back to slowly or moderately reactive aggregates. There's not a lot of, we're not putting these in field exposure blocks, right? Because we're not having problems with, nobody cares, except Jason Eidecker cares. Jason Eidecker is going to do this now. So it'll be good to have that data and throw some things in there to see what that does. These are the references. We've got a few publications from my dissertation work out there. Janny has some work with her grad students, and like I mentioned earlier, there's a publication forthcoming with Eric on there. This is our new ERDC conclusion slide, where you get to look at a lot of faces. I'm not sure if they consented to this, but there they are. All right, thank you.